Okay, Bismillah. Bismillah. Okay, I want to discuss about topics on measurable function. Topic on measurable function. Okay, first let's start. Suppose, we have a two measurable space. Measurable space. That be this one, our first measurable space, and then we will have the second. Second measurable space. So what the meaning of measurable space? Measurable space is just a pair. Pair of a set and also algebra or sigma algebra on set. Such of pair here we call it as a measurable space. And then so supposing we have two measurable space, and then let be the first measurable space any measurable space, and then the second one let be a specific measurable space. What the meaning of any measurable space? Meaning that our x here can be any. Our x here, what is the x? X meaning that this x is just a set. Can be any set, can be finite, can be countable or uncountable set. Of course, this sigma algebra defined on x. But the second measurable space here, we have a specific one. When we consider our x will be the set of real numbers, and then this borrowed sigma algebra is just a sigma algebra defined on the set of real numbers. So now let be a mapping. So we have a mapping, let be such a mapping that map from x to r. So now we have a mapping that map from this set x to the set of real numbers. Of course, such a mapping here already well known by all of you. So this mapping is called function, or some textbook they use real valued function. Or you can call it as a function. Just a short, short term. Of course you can construct, you can define a lot of function. When you say about function, you mean that you define such a mapping that map from this set x to set of real numbers, and you can consider a lot of function. So today we want to discuss such function here is called measurable. Meaning that if we consider any function, now we just want to select or we want to choose such a function here to be measurable. Of course, such a function we want to discuss today is called measurable function. Definition. A function is called measurable it's called measurable if satisfy this condition. Okay, if satisfy such condition that for any borrow set, okay, for any borrow set, then you can find the pre-image of this borrow set inside of sigma algebra. Okay, so such a function is called measurable if satisfy this condition. Okay, meaning that when you consider, okay, when you take any borrow set, okay, and then you find the pre-image of this borrow set, this pre-image of borrow set should be inside of sigma algebra. Okay, of course, when you consider any borrow set, okay, what do you mean of borrow set? Borrow set meaning that element of borrow sigma algebra. Okay, and you consider all borrow set. All borrow set meaning that you consider all elements of borrow sigma algebra, and then you find the pre-image of all elements of this borrow sigma algebra. This pre-image of all element of borrow sigma algebra should be inside of sigma algebra. Of course, this borrow sigma algebra is from the second measurable space, and this sigma algebra is from the first measurable space. Okay, so therefore we call it, our function here is measurable. Of course, we can just define a lot of function that map from x to r, and from this function we just want to check, or we just want to choose or select such a function here to be measurable. Okay, if you want to select such a function to be measurable, it should be satisfied this condition. Okay, another thing, when you want to check such a function here measurable, of course from this definition you need to do two things. Okay, you need to understand, okay, the two things. Okay, when you understand these two things, then of course you can check this condition. Okay, the first thing that you need to understand, and then you need to understand how to find, okay, the pre-image of all borrow set. Okay, so this is the first thing, the very important thing you need to understand, and then you need to know how to find pre-image of all borrow set. And then the second thing, you just check this pre-image of all borrow set, is it inside of your algebra or not? Okay, of course, if the condition that it satisfies the condition that pre-image of all borrow set inside of algebra, so then you can say that your f here is measurable. Okay, of course your f here measurable with respect to algebra. Okay, meaning that the measurability of your function here depend the choice of your algebra. Okay, the selection of your algebra. Okay, later we will see examples. So I will present to you examples of measurable function and also non-measurable function. Okay, so this is just a brief to understand, okay, what the meaning of measurable function. Okay, let's consider example. Okay, first example. Okay, let be x here the set of E. Okay, set with element here. Okay, we have three elements A, B, C. Okay, so we have a finite set. Okay, of course from this set already discussed before, we can define five algebras on the set of three elements here. Okay, if you remember. Okay, so let list the five algebras can be defined on this set. For example, F1. Okay, so F1 we will have empty set X. Okay, so this one is the smallest algebra. Okay, and then let be F2 is a power set of our X. Okay, so what do you mean of power set of X here? Meaning that we have the set of all the collection of all subset of X. Okay, that be power set here. Of course, the power set of X is the largest algebra, and then we have the third algebra. Okay, so I will have this one. Okay, so this one also is algebra. Okay, on X here, and you can check the condition to be algebra, and this F3 is satisfied such condition. Okay, and then we have a F4. Okay, this one also is algebra, and then we will have F5. Okay, so we will have 5 algebras. Okay, algebras on this. Okay, so now we have these 5 algebras. Okay, let this please. Okay, first example. Okay, let's consider such a function here, f1. Okay, let me f1 is the first example. Okay, function for first example. Okay, so now I will have a function f1 that map from this x to r. Okay, x to r. Okay, let us define our f1 as follows. Let be f1a is equals to f1b is equals to f1c. Okay, let be equals to 3. Okay, let be equals to 3. Okay. Okay. So this f1, okay, is well known by all of you as a constant function. Okay, constant function meaning that you only have a one single value. Okay, for this function. Okay, when it maps to all elements of x. Okay, so such a function here we call it as a constant function. Okay, meaning that this function only takes one value. So I can say that from here, I can say that when I consider function of all set x here, so this one is only equals to 3. Okay, so this one. Okay. Okay, so now, okay, from this function f1, okay, so let's try to find all possible pre-image of this f1. Okay, all possible first. Okay, all possible pre-image of f1. Okay, so what do you mean of pre-image? Pre-image meaning that you need to find such mapping, right? Okay, such mapping. Okay, so I will denote this one. Okay, minus 1 here. Inverse. Okay, inverse function, or we call it this one as a pre-image. So we consider a pre-image meaning that you need to map from R to X. Okay, from R to X. Okay, from R to X. Okay, so this one is a pre-image. Okay, meaning that when you consider the image or function function f1 map from X to R, when you consider pre-image or inverse function, meaning that you will map from R to X. Okay, Okay, so now let's discuss all the possible of this inverse, okay, or all possible of this pre-image. Okay, since our function f1 only takes one value, meaning that this f1x, okay, maps to all element of x here, it only takes one value equals to 3. Okay, so therefore I can say that inverse of 3 is equals to 1. Inverse of 3 will be equals to this set A, B, C. Okay, why? Because you see FA is equals to 3, FB equals to 3, FC and F1C equals to 3. Of course, when you take the inverse of 3, will give you A, B, and C. Okay. 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 So now we have a inverse of 3 is equal to this one. Okay. So therefore, this one is equals to x. Okay. Okay. Now, if I consider that such of number, okay, let be y here. Okay, such of number not equals to 3. Okay, not equals to 3. Or I can say that I will take all values of y here from this element. Okay, from this set. Okay, this set. Okay, difference 3. Okay, so I will consider such of number. Okay, such of number here not equals to 3. Okay, so I can say about inverse of y. Okay, for all y is taken from this set. Okay, so this one equals to 1. Okay, since our f1 here takes only one value, 3. Okay, meaning that our f1 doesn't take any value other than 3. Okay, therefore, when you find the pre-image or when you find the inverse of this y, okay, where this y is taken from this set, so therefore this one is equals to empty set. Okay, equals to empty set. Okay, why? Because you see, when you map f1 to x to r, so you have something like f1a equals to 3, f1b equals to 3, f1c equals to 3, right? Meaning that you don't have other number than 3. Okay, therefore when you find the pre-image and inverse of y, where y here is not equals to 3, so therefore this one equals to empty set. Okay, so now you have two possibles of pre-image or inverse of this function f1. Okay, so meaning that you have two. Okay, two inverse, two possible inverse of f1. Okay, either equals to x or equals to empty set. Okay. Okay, so now. Okay, now we want. Okay, what our objective? What our purpose now? We want to check that our f1 here is measurable. Is it? Okay. To check such that f1 here is measurable, meaning that our f1 should be satisfy the condition to be measurable. Okay, the condition that already mentioned, discussed in definition. Okay, so meaning that the first thing you need to find. Okay, you need to find. Okay, meaning that if you consider all border set, okay, then you need to find this pre-image. Okay, pre-image of all border set. Okay, you need to find this one. Okay, meaning that we need to find all pre-image. We need to find the pre-image of all border set. Okay. Okay, so since we have such value, okay, value of the function only 1 is equals to 3. Okay, first of all, before we go to this part, okay, pre-image of B. Okay, first let us recall what the meaning of border set. Okay, border set here is just a element of border sigma algebra. And then in the previous class, okay, I already show we have types of border set. Okay, such type of border set. Okay, meaning that I already show in the previous class we have this one. Okay, such of interval here is a border set, and this one also is a border set. Okay, and then what else? Okay, this one also is our border set. Okay, and then this one is also border set. Okay, and then okay, this one also is a border set. This one is also okay, this is border set. Okay, this one is a border set, and then this one also is a border set. Okay, so we have a okay, this type of border set. Okay, this interval. Okay, and I already showed in the previous class. This one is a border set, meaning that this one, this all the interval here is a element of our border sigma algebra. Of course, we have infinitely many values. We have infinitely many of border set. Why? Because we will consider such of A, B here. Okay, we consider such of A, B here. All element from real number. Okay, the set of real number. Okay, because of that, we have infinitely many. Okay, infinitely many of border sets. Okay, but now you see, in this definition, you need to find the pre-image of all border sets. Okay, of all border set, meaning that you need to consider this infinitely many border set, and then you need to find the inverse. You need to find the pre-image. Okay, so meaning that, okay, of course you need to consider all pre-image of all border set here. Okay, because from definition say that for all border set we need to find the pre-image. Okay, okay. So now, how we want to find? Okay, how we want to find the pre-image of all border set here? Okay. Okay, now I will consider okay, some example of border set. Okay, let's consider this border set. Okay, let's consider this border set. Okay, minus 3, 1. Okay, let's consider minus 3, 1. Okay. Okay, so from this minus 3, 1, okay, let's find this one. Okay, so this one. Okay, what is the inverse function? Okay, what is the inverse of f1 for this border set here? Okay, so meaning that, you see, in this interval, okay, when you consider all values on this interval, meaning that this value is not equals to 3. Okay, because 3 doesn't inside of this border set. Okay, so therefore I can say that this one is actually empty set. Okay, empty set. Okay, because of what? Because in this interval, okay, in this border set doesn't contain 3. Okay, of course, when you find the pre-image or inverse of this value, all values inside of this interval will be empty set. Okay. Okay, now let's consider this one. Okay, such of interval, such of border set. Okay, for example, I will consider this one. That will be 0 and 4. Okay, 0 and 4. Okay, so now, okay, let's consider this pre-image. Okay, this inverse function here. Okay, so this one. Okay, so in this border set, in this interval, does it contain 3? Okay, so you have 3 inside of this interval, right? Okay, so therefore, from here, I can write something like this one. So from here I can write something like, okay, so f1, okay, minus 1. Okay, now I will have this one. Okay. Since this interval, this border set, we have 3, meaning that I can write something like this one. Okay, 0, 3, and then open, and then union, 3, and then union, 3, and 4. Okay, this one. Okay, so this one actually same with this one. Okay, but now I will consider this one equals to this one. Why? Because since our f1 have value 3 here, okay, I just let this interval separate into these 3. Okay. Okay, of course from here, okay, from here I can write, okay, I can write this part is equals to this one. Okay, we have this property. Okay, 0, 3, okay, and then union f1 minus 1, okay, 3, okay, and then union f1 minus 1, okay, 3, 4. Okay, so this one. Okay, we have a such a property say that if f, okay, pre-image of A union B, okay, so this one is actually equals to pre-image of A and then union pre-image of B. So therefore, from this one, I can write something like this one. Okay, now you see, what the pre-image of this interval, this border set, 0 and 3. Okay, meaning that you will consider the pre-image of all values in this interval. Of course, in this interval doesn't have 3, right? So therefore, this one is equals to empty set. Okay, how about this one? What the pre-image of 3? Okay, pre-image of 3 here meaning that pre-image of this value. Okay, because we have only single value 3 here. So what is this one? Pre-image of this one. So this one is equals to x. Okay, so how about this one? Pre-image of 3, 4, meaning that we find the pre-image of all values in this interval. Since this one we don't have 3. When we don't have 3 means that this one is the empty set. Okay, empty set. So therefore, from here we will have empty set union x, union empty set. So therefore, this one is equals to x. Okay, this one equals to x. Okay, so from this example, okay, these two example, I show you such of types of border set. Okay, meaning that the first example here, such of types that border set doesn't contain 3. Okay, this example. Okay, this example. Okay, that's okay. I'll just write this one. Okay, this is the example types. This example type of border set, okay, doesn't contain 3. Okay, and this is the border set. Okay, this is example of border set that contain 3. Okay, that contain 3. Of course, you can consider a lot of such a border set. Okay, doesn't contain 3. For example, you can consider 2 or 3 example. Okay, you can just construct such of interval here doesn't contain 3. Okay, and also you can consider another example. Okay, such of interval that contain 3. Okay, so you can consider a lot of example such of interval that doesn't contain 3 and such of interval here that contain 3. And then if you find the pre-image, okay, if you find the pre-image of all this example, okay, it will give you the same pre-image, which is empty set. okay, which is empty set. And of course, if you consider another examples of interval, okay, that contain 3, okay, that contain 3, of course, when you consider when you find the pre-image of this interval, pre-image of this borrow set, it will give you the same, okay, the same pre-image, which is equals to x. Okay. If you don't believe, if you don't trust me, then I will suggest you try to consider. Okay, try to consider 2-3 examples of interval that doesn't contain 3. Okay, and then try to find the pre-image of all these examples. It will give you the same equals to empty set. Of course, you can consider also 2-3 examples of interval that contain 3. And of course, when you find the pre-image of this interval, it will give you the same answer equals to x. Okay, you can consider. If you don't trust me, if you don't believe me. Okay. Okay. So therefore, sorry, this one I forgot. F1. Okay, so from this one, then I can conclude. Okay, I can conclude that if I consider all borrowed set here, okay, of course my borrowed set here we have infinitely many. If I consider all borrowed set here, and then I find the pre-image of all borrowed set for this function f1, I will have 2 pre-image. Okay, I will have 2 pre-image. The first pre-image is equals to empty set if my borrow set, okay, my borrow set doesn't contain 3. And the second one is equals to x if my borrow set contain 3. Okay, this one. Okay, of course, this one will be pre-image of first example. Okay, first function example for all borrow set. Okay. Okay, like I said before, when we consider all borrow set, meaning that we have infinitely many. Okay, infinitely many borrow set. But when we check the pre-image of all borrow set, we can come to the conclusion that we will have two pre-image. Okay, 2 pre-image. Okay, meaning that when you have a 2 pre-image here, meaning your all borrow set here, okay, infinitely many of all borrow set here, you can categorize it. Okay, you can group it into 2 groups. Okay, 2 groups. The first group, we consider the collection of all borrow set doesn't contain 3. Okay, of course, when you find the pre-image of all this borrow set that doesn't contain 3, they will have the same pre-image, which is empty set. Okay, and then you will have the second group of the borrowed set, where you consider all borrowed set that contain 3. And of course, when you find the pre-image of all these borrowed set, okay, that contain 3, they will have the same pre-image, which is equals to x. Okay, so this one. Okay, of course, like I said before, if you don't believe me, okay, if you don't trust me, then you can consider. Okay, you can just construct, okay, a lot of example, such of intervals that doesn't contain 3. Okay, and then you find the pre-image here. Okay, so the answer should be same equals to empty set. Okay, you can check. Okay, if you don't believe me, if you don't trust me. Okay, of course you can consider such of interval that contain 3. Okay, you can consider a lot of example of interval that contain 3. And then you can check if you find the pre-image of this interval, they will give the same interval, the same pre-image, which equals to x. Okay. Okay. Of course, if you feel that maybe, okay, maybe you cannot see, or maybe you still cannot see, you cannot understand how I come to this empty set and x if b doesn't contain 3 and if b contain 3. So I suggest to you that you consider. okay, some examples, okay, some examples of border set that doesn't contain 3, and also some examples that contain 3, and then try to find the pre-image of this interval. Okay. Okay, so of course the first part, okay, we already have the pre-image of f1 of all b here. Okay, so meaning that we have 2 empty set and also x. Okay, so now we want to check. Okay, we want to check either our f1 here is measurable or not. Okay, of course our f1 here is measurable by definition. It should be meaning that you want to check your f1 here is measurable or not. It should be depend on the choice or selection of algebra. Okay, of algebra. Okay, so now, okay, let's consider first our f1. Okay, before this, our f1 is empty set and also x, right? Okay. Okay, so now what I want to check here now. Okay, so now I want to check either my f1 is measurable with respect to this sigma, this algebra, yes or no. Okay, yes or no. Okay, meaning that I need to check the condition that all the pre-image of f1 here should be inside of this one. Okay, so you see, I already find the all pre-image of f1 for all pre-image of f1 for all border sets. So we have 2 empty set and also x, and then it shows that this empty set is element of f1. This x also is element of f1. So meaning that from this, okay, meaning that from here, it shows that f1, okay, pre-image of all border set here is element of f1. Okay, for all border set. Okay, because you see, empty set is element of f1, x also is element of f1. Okay, so therefore, our conclusion here, f1 is measurable, okay, with respect to this algebra. Okay, f1. Okay, so now let's consider f2. Okay, let's check f2. What is our f2? f2 is a power set of x. Okay, power set of x. Okay, you can list. Okay, you can list the power set of x here. What is the power set of x? Okay, now let's check. Either pre-image of all border set here inside of f2, yes or no? Okay, so now we have this pre-image of all border set, empty set and also x. Of course, empty set here is element of f2. X also is element of f2. So meaning that the pre-image of all border set here is element of f2. So when you have the condition, that pre-image of all border set here inside of f2. So therefore, f1 is measurable, okay, with respect to f2. Okay, algebra. Okay, same f3. Okay, oh sorry, this one should be f2. Okay, let's check for f3. Okay, f3. Why is that f3? f3 we have empty set, x, and then we have a, and then we have b, c. Okay, so this one. Okay, so now let's check either f1 is measurable with respect to f3, yes or no. Okay, so meaning that we need to check the pre-image of all border set here should be element of f3. So now, see, we have empty set is element of f3. X also is element of f3. Therefore, our f1 is measurable with respect to this algebra. Okay, next let's consider F4. Okay, algebra, fourth algebra. What is a fourth algebra? Okay, fourth algebra. So for algebra, I think I have this one, right? Okay, so I will have B, and then I will have E here. Okay, B and E. See. Okay, so now we want to check our F1, is it measurable with respect to this algebra or not? Okay, so now we have the pre-image of all borrow set is empty set and also X. You see, empty set is element of this algebra. X is element of this algebra. Okay, so therefore meaning that F1 also is measurable with respect to this algebra. Okay, this algebra. Okay, then the last one. Okay, the last one, F5. Okay, F5. So F5, we have this collection. Okay, so now let's check. Either the pre-image of all borrow set here, is it inside of this algebra? Yes or no? Empty set, is it element of this algebra? Yes, we have. X, is it element of this algebra? Yes, X. Therefore, F1 here is measurable with respect to F, this algebra. Okay, so it shows that when you consider such a function here, F1, okay, what is the F1 here? F1 here is equals to 3 for all element of X. Okay, so such of F1 here is a constant function. So meaning that such a constant function here is measurable with respect to all algebra. Okay, we can say that a constant function is always measurable. Okay, it's always measurable. Because of what? Because the constant function, we show that from this example, is measurable with respect to all algebra. Okay, because you can see or you can check when you consider a constant function. For the constant function, they only have two. They only have a two pre-image for all borrow set, which means empty set and also X. Of course, by the definition of algebra, what's the definition of algebra? The first condition to be algebra, the collection here should be contain empty set and also X. Okay, and then of course when you consider the pre-image of constant function, it always give you empty set and X. Empty set is element of algebra. X also is element of algebra. Therefore, we can say that the constant function is always measurable. Okay, constant function is always measurable. Like just now, I say that what the meaning of constant function is always measurable, meaning that our constant function is measurable with all is measurable with respect to all algebra. Okay, so corollary. Okay, constant function constant function meaning that we have fx is equals to c. Okay, there is some number here, fx equals to c, meaning that when you mapping all elements of x here, it will give only one value here, c is constant function here is always measurable. Okay, so meaning that our fx is equals to c is measurable with respect to all algebras. Okay, all same algebras. Okay, so Okay, so for the constant function, we don't need to worry to find, okay, such of constant function to be measurable, okay, because when you have a constant function here, by this corollary, we say that all constant function here is always measurable. Okay. Okay. Now let's consider the second example. Okay, so now let the x here, okay, same, x, a, b, c, okay, but now, okay, let's define such a function of f2. Let be f2 here is a function that map from x to r, okay, so I will consider the second example, second function here. Okay, so now I will define my f to a here, okay, f to a here, let be equals to, okay, f to a here, let be equals to 4, okay, and then let be f to b, okay, let be f to a is equals to 4, f to b equals to 2, and then f to c is equals to 4, okay, okay. So now, so we have f to a equals to 4, f to b equals to 2, f to c equals to 4. Meaning that, so our function, okay, takes two values. Okay, from here we can say that our function here, f2, it takes two values, which is 2 and 4. Okay, 2 and 4. Okay, so now we have the two values. Okay, different with the first value. First value is just a constant function. We have one value, but now for f2 here we have two values. Okay. Okay, so now let's consider all possibles of this of pre-image of f2. Okay, or I can say that we consider all possible inverse. Okay, of f2 here. Okay. So what the meaning of inverse of f2, or what the meaning of pre-image of f2 here? Meaning that we need to, okay, find all possible of such of mapping that map from R to X. Okay, so this one. Okay, so let's find all possible of such mapping here. Okay. Okay. So first, okay, so since we have two value, okay, so we have a two value here, okay, fx here is equals to 2, 4. Okay, first, okay, sorry, f2. Okay, so first, let's consider the this possible, okay, inverse of, okay. Now, since we have 2 and 4, okay, let's consider 2. Okay. So what is the inverse function of 2 here? Okay, since we have only 1 here, okay, b, right? Okay, so this one is b. Okay. Okay, next, the possible of inverse. Okay, next possible inverse. So f2 minus 1, and then we have 3. Okay. So what is 3 here? Okay, so 3 here will give me, okay, sorry, not 3, 4. So 4. Okay, what is 4? So I will have E and C. So therefore I will have this subset, E and C. Okay. Okay, what are the possible inverse that you can find here that map from R to X here? Okay, for example, if I consider such of Y, okay, all Y okay, from this set, okay, y from this r, okay, and then difference 2, 4, okay. So meaning that I will consider such of value that other than 2 or 4, this one, okay. So if I consider all y from this element, from this set, okay, so I can say about f2, okay, f2 minus 1, this one, okay, so this one equals to 1. Okay, of course this one is equals to empty set, okay, because of what? Because your function here doesn't take other value than 2 and 4, okay. For example, if I take my y here is equals to 3, okay, is equals to 3. Of course, y pre-image or inverse of 3 here is empty set, okay, because our function f2 here only takes 2 and 4, okay. So therefore, if I consider y here that taken from this element, from this set, okay, of course, so my y here will not equals to 2, y also not equals to 4. Then if I find the inverse of this, y should be empty set, okay. So this is the possible, okay, I can say the possible of the inverse, okay, of the inverse here, okay, that we will have, okay. Okay, so now we want to check f2 here, is it measurable or not, okay, meaning that by the definition, okay, by the definition, so by the definition here, you need to find the pre-image of all border set, okay. Now we need to find the pre-image, okay, of all border set, okay. Of course, we consider the second example here, okay, f2 here, okay, b. Okay, let's consider, okay, since we have 2 and 4 here, okay, we have a 2 and 4 here. Okay, first, let's consider such of border set, okay, doesn't contain 2, and border set here, okay, border set that doesn't contain 2 and also doesn't contain 4, okay. So we consider such border set here, okay, meaning that such a border set, such of interval here doesn't have value of 2 and so also doesn't have value of 4, okay. For example, okay, let's consider this example, minus 1, minus 1, 1, okay, for example this one, okay. Of course, this interval, okay, doesn't have 2 and also doesn't have 4. Okay, now what is the pre-image of this interval? Minus 1, 1, okay, minus 1, 1. Okay, of course, since this interval doesn't have 2 and doesn't have 4 here, meaning that if you find the pre-image of all values from this interval, okay, it will always give you empty set, okay, because we already discussed, right, the possible inverse, okay, for this f2 here. When you take your y here, it's not equals to 2, it's not equals to 4, it always empty set. So this one is equals to empty set, okay. So meaning that if my border set here, okay, doesn't contain 2 and doesn't contain 4, then I can say that my pre-image of B here is empty set, okay. So this one, okay, you can consider, okay, you can consider a lot of example and then try to check, okay, the pre-image of this interval. Okay, so this is the first one. Okay, the second one, okay, now I will consider such of border set that contain 2 but doesn't contain 4, okay. B doesn't contain 2 B here contain 2, but B here doesn't contain 4. Okay, for example, I will consider such of border set. Okay, such of interval. Okay, let be 1.5 and then 3. Okay, for example, this interval. Okay, of course, this interval, this border set here will have 2, but doesn't have 4. And then you can see this one. Okay, this pre-image of this one actually is equal to this one. Okay, I will not show you how. Okay, you can check by yourself. Okay, this one actually equals to this one. Therefore, what is the pre-image of these two? Inverse of 2 here. So inverse of 2 here is equals to B. Okay, equals to B. Okay, it's okay. You can just put this one. Okay, B. Okay, just single element B here. Okay. Okay, so how about number 3? So number 3. Okay, second here I consider ball set contain 2, but ball set doesn't contain 4. Now number 3 here I will consider that my ball set here contain 4, but my ball set here doesn't contain 2. Okay, doesn't contain 2. Okay, this example. For example, okay, which interval that have this condition here? Meaning that you have 4 but doesn't have 2 here. For example, if I consider 3, 5. Okay, 3, 5. This interval. Of course, this interval doesn't contain 2 but contain 4. So what is the pre-image here? So therefore, when I find the pre-image of this interval, actually this one will give us F2, 4. Okay, you can check. This one, actually this one. So what is the 4 here? So this one will give me AC. Okay, AC. Okay, and then the last one. Okay, so I have B doesn't contain 2 and B doesn't contain 4. The second one, I have a B contain 2 but B doesn't contain 4. And then number 3, I have B contain 4 but B doesn't contain 2. Okay, so the last one, I will consider such of ball set that this ball set contain 2 and this ball set also contain 4. Okay, meaning that such a ball set here have two value. Have these two value, 2 and 4. Okay, so for example, okay, if I consider this example, okay, let be 1, 5. Okay, 1, 5. Meaning what the meaning of 1, 5 here? Meaning that I have 2 and also I have 4 in this interval. So what is the pre-image of this interval? So therefore this one, I can write this one actually is equal to this one. So I will have 2 and 4. Okay, you can show. Okay, you can check. This pre-image of this interval actually is equal to pre-image of this one, 2 and 4. Okay, meaning that 2, 4 here. So since 2, 4 here, I can write this one as 2 union 4. Okay, so when this one, okay, by properties, I can write this one is union F2 minus 1, 4. So therefore the last one I will have, what is 2? 2 is B. And then what is this one? AC. Okay, AC. So therefore this one is equals to X. Okay, it's equal to X. So the pre-image for this ball set that contain 2 and contain 4 is equals to X. Okay, so we will have only 4 types. Okay, 4 types of border set here. Okay, when you consider such a function here takes two values, 2 and 4. Okay, so meaning that first type of border set, you consider that this border set here contain 2, doesn't contain 2 and also doesn't contain 4. Okay, so I show you one example, and from this example you can check the pre-image for this type of border set. The first type of border set is empty set. Okay, and then the second one, I consider such a border set here that contain 2, but this border set doesn't contain 4. Okay, I already show you one example, such of interval here that contain 2 only, okay, but doesn't have 4. Okay, and of course when you check the pre-image of this interval, you can check actually this pre-image of such of interval here will be equals to pre-image of 2. Okay, pre-image of 2, therefore pre-image of 2 only B. And then for the third types of border set, so we can consider such a border set here that contain 4 but doesn't contain 2. Okay, I already show you one example of this border set, and you can check pre-image of this interval that contain 4 but doesn't contain 2. So this one is equals to pre-image of 4. Okay, when you have a pre-image of 4, of course this one is equals to AC. And then the last type of border set, you will consider such a border set here contain 2 and contain 4. Okay, like this example. Okay, 1, 5 here. Okay, so 1, 5 here you have 2 and you have 4. Therefore, this pre-image of this interval 1, 5, I can write this one is a pre-image of 2 and 4. Okay, 2 and 4. Okay, we have a 2 element, 2 and 4. So 2 and 4 here I can write as 2 union 4. Then by using these properties, so I will have pre-image of 2 union pre-image of 4. So what is the pre-image of 2? Pre-image of 2 is equals to B. And then what is the pre-image of 4? Pre-image of 4 is equals to AC. Of course, B union of AC here is equals to X. Okay, for the fourth type, for the type number 4 here, border set. Okay. Okay, so now come to the conclusion. Okay, so I can conclude that okay, for all border set, okay, then this pre-image, okay, I consider the second function. Okay, example from the second function. This pre-image will give me 4. Okay, I have a plot 4 pre-image for functions in the second example. So this one is equals to empty set if my B here doesn't contain 2 and B here doesn't contain 4. Okay, the second one is equals to B if my B here contain 2 but okay, B here okay doesn't contain 4. And then this one is equals to AC if B here contain 4 but B doesn't contain 2. And then the last one is equals to X if B here contain 2 and B contain 4. Okay, so this one. Okay, so meaning that if you consider all border set here, okay, from the second example, function in second example, you find the pre-image of all border set here, you will have 4. This 4 meaning that you have empty set, you have B, you have AC here, you have X. Empty set if B here doesn't contain 2 and B here also doesn't contain 4. B here if B here contain 2 but B doesn't contain 4. AC here if B contain 4 but B doesn't contain 2. And then this one equals to X if B here contain 2 and B here also contain 4. Okay, so from this function, second example here, you see from infinitely many border set here, I will divide here into 4 groups. Okay, I will divide here into 4 subset. Okay, the first subset, the first collection, I will consider all border set here doesn't contain 2 and doesn't contain 4. Okay, first group, okay, or first subset. And then the second subset, I will consider the collection of all border set here, but now I have 2, okay, that contain 2 but doesn't contain 4. And then the third subset, okay, I will consider all border set here, but now this border set, the collection of all this border set here, such that that border set here contain 4, but border set here doesn't contain 2. Okay, and then the last subset, I will consider such a border set here that contain 2 and contain 4. Okay, so from this function, the second example function here, now my border set here, I will consider 4 groups, okay, 4 subset of border set here. Okay, and when you check, okay, for example, you consider 2 or 3 or 4 example from the first group, okay, from the first subset. Okay, if you don't believe me, if you don't trust me, okay, you can check, you can try to select some example from this first group, and then you find the pre-image of this border set. All of it will give you empty set. Of course, if you consider some example, 2 or 3 example, okay, you take from the second group of border set here, okay, which contain 2 but doesn't contain 4, okay, and then you find the pre-image of this border set, okay, it give you the same, okay, it give you the same answer, which equals to B. Okay, and still, if you don't believe me, if you don't trust me, okay, you can select some example from the third group, which the third group here, that border set here contain 4 but doesn't contain 2, and then you find the pre-image here, so it will give you the same pre-image AC. Okay, and then the last one, if you feel still not comfortable with my answer here, okay, you can just find, you can just select some example from fourth group where you consider some interval that contain 2 and 4, and then you find the pre-image. They will give the same pre-image which equals to X. Okay, so you can check this one. Okay, meaning that for the second example here, where you find the pre-image of this B, okay, for all border set here, it only have 4 pre-image. Okay, it will be not less and will be not more than 4. Okay, so it will have 4 pre-image. Okay, for the second example. Okay, so now let's check. Okay, so first thing, okay, we have the pre-image here. Okay, pre-image for all border set here. But now we need to check for the second part. Does this all pre-image here inside of algebra? Yes or not? Okay. Okay, let's consider the F1 here. Okay, first let's consider the first algebra. So the first algebra here is empty set and X. Okay, you see, empty set is element of F1. B here is not element of F1. So you see, when you have a B here, is not element of F1. So meaning that my second function here is not measurable. Okay, it's not measurable with respect to F1. Okay, algebra, first algebra. Okay, why? Why is not measurable? Because the second, the definition of measurable say that you need to check all pre-image here. Okay, you need to check all pre-image here should be element of algebra. Okay, so now you see only one pre-image. It doesn't belong of my F1 here, my first algebra here. Okay, so therefore F2 here is not measurable with respect to F1. Okay, so now let's consider F2 here. F2, second algebra. Second algebra, we have power set of x here. Right, okay, power set of x. Okay, power set of x. Okay, so power set of x here. Okay, let's check. All pre-image here. Is it inside of second algebra? Yes or no? Okay, empty set. Okay, inside of power set. B, inside of power set. AC, inside of power set. X also is power set. Meaning that all pre-image here is element of power set X here. So therefore, F2 is measurable with respect to second algebra. Okay? Because of what? Because what the meaning of power set X here? Meaning that you have the collection of all subset of X, right? So empty set, element of Px. B, element of Px. AC is element of Px. X is element of Px. Okay? All pre-image here is element of this algebra. Therefore, we say that, Therefore, we say that the second function here is measurable with respect to second algebra. Okay, so let's consider the F3. What is this F3? So third algebra. Third algebra will be empty set X, A, and BC. Okay, so this one. Okay, let's check. Empty set. Empty set. B. Do you have B in F3 here? The third algebra here. Okay, so you don't have. Okay, B here you don't have in third algebra. So, meaning that the second function here, and function in second example, is not measurable with respect to F3. Okay, because you can see only one. Okay, only one pre-image doesn't belong to algebra. Therefore, it destroy the condition of definition of measurable. Okay, so meaning that F2 here is not measurable with respect to third algebra. Okay, let's consider the fourth. Okay, the fourth here, so you have B, and then you have AC. Okay. Okay, now let's check this one. Okay, empty set, you have empty set. B, do you have B? Okay, you have B here. AC, do you have AC inside of fourth algebra? Yes, you have AC. X, do you have? Okay, X. Okay, meaning that all pre-image here belong, or you can find inside of fourth algebra. Okay, so therefore F2, okay, F2 is measurable with respect to fourth algebra. Okay, because all pre-image here inside of this algebra. Okay, last F5. So F5 we have empty set X. Fifth algebra we have C. We have AB. We have AB. Okay, let's check F2 here. Is it measurable with respect to fifth algebra? Yes or not? Okay, empty set you have B. Do you have B in fifth algebra here? So you don't have that. Okay, so B here don't have in fifth algebra. Okay, so meaning that your second function here is not measurable with respect to fifth algebra. Okay, fifth algebra. Okay, because of what? Because you can find one pre-image. Okay, one pre-image here doesn't belong to this algebra. Therefore, it destroy the condition of definition, the condition of measurable definition. So this one is not measurable with respect to fifth algebra. So in the end, okay, we say that F2 Okay, F2 is measurable with respect to second algebra and fourth algebra. Okay, the second one here is the power set, and 4 here is this one. Okay, so this one. Okay, of course F2 here is not measurable with respect to F1. It's not measurable with respect to F3. Third algebra, first algebra, and also fifth algebra. Okay, so this function is only measurable with respect to second algebra and also fourth algebra. Okay, because the condition that all the pre-image, okay, pre-image of all border set here inside of that algebra. Okay. Okay. So now, okay, so I will give you one example. Okay, maybe this one is your home task, home exercise. You don't need to submit this one. Okay, you don't need to submit this one. Okay, let be that example. Okay, home task or home exercise. Okay, let be this one is your own. Okay, own exercise, your own effort. Okay, try to understand. The meaning of measurable function itself, and try to see the example of measurable function and also non-measurable function. Okay. Okay, so now I will consider my axial. Okay, let me my axial is A, B, C. Okay, then my A, B, C here. Okay. Okay. Okay, so we will have these 5 algebras. Okay, now I will define such of mapping here. Okay, fx to real number here. Okay, such that my f3a is equals to -1, f3b is equals to 2. Okay, let be 5. Okay, let be f3c is equals to -7. Okay, so this one. So meaning that my f3x, okay, my f3x here have 3 values. Okay, have 3 values, meaning -7, -1, and also 5. Okay. Okay, -7, -1 is also 5. Okay. Okay, so now I ask you, okay, the question is, which algebra, atau algebras, which algebras that which algebra that satisfy, which algebra that satisfy which algebra that make which algebra which algebra Which algebra? Apa ayatnya? What's the sentence? What's the question? Okay, which algebras make, okay, which algebras I don't know, maybe which algebras that make, okay, 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 which algebras imply, okay, which algebras, okay, implies, which algebra imply, okay, which algebras imply that, okay, F3, which imply that F3 is measurable. Okay, which algebras imply that F3 become good. Okay, which algebras imply that F3 become, okay, becomes measurable. Okay, okay, which algebras imply that F3, okay, your function here, okay, becomes measurable. Okay, which algebras imply that F3 becomes measurable. Okay, you maybe my question here. Okay, actually I will ask you to see. Okay, I ask you to see. So our F3 here, okay, the example here is measurable with respect to which algebra? Okay, which algebra? Okay, because we have 5 algebra, right? Okay, for x equals to a, b, c, we have 5 algebra. So now such a function here is defined by this one. Okay, so we have 3 values here, and then I ask you to see, okay, to check our F3 here is measurable with respect to which algebra? Okay, which algebra? Okay. Okay. Okay, I show you. Okay, example here. Okay, I just give you some hint. Okay, some hint here. For example, we have 3 values here, right? Okay, we have 3 values here. Okay, now you want to find such, okay, let's consider borrow set. Okay, so now you want to find the p-image for all borrow set here. Okay, so F3. Okay, so you can consider 8 types of borrow set. Okay, 8 types of borrow set. Okay, the first borrow set, of course, you consider that B here doesn't contain -7, B doesn't contain -1, and then B doesn't contain 5. Okay, so it's 5 right? 5 okay, tak apa. Okay, 5 here. Okay, so it's fine. So from here, what is the pre-image of this borrow set? Okay, this type of borrow set. Okay, and then the second one, you can consider such a borrow set here that contain -7 but doesn't contain, okay, doesn't contain -1 and 5. Okay, or actually I can say okay, doesn't contain -1 doesn't contain -5. Okay, so if I consider such of borrow set here, so this one equals to what? Okay, then number 3, I can consider such of borrow set here. For example, doesn't contain -7 but contain -1 and contain -5. Okay, so this one. So what is the pre-image of this borrow set? Okay, this one. Okay, so meaning that you need to consider all types of borrow set here. Okay, all types of borrow set. Okay, 4, 5. Okay, of course, when your function here have 3 values. Okay, when your function here have 3 values, then you can consider 8 types of borrow set. Okay, number 5, number 6, number 7, number 8. Okay, number 8. Okay, so you can consider another types of borrow set and then try to find this pre-image. Okay, pre-image of all these types of borrow set. Of course, when you have you have a function with 3 values here, then you will have 8 pre-image here. Okay, you will have 8 pre-image. Okay, for F3 here. Okay, so I will ask you to find this one. So I will ask you to find this 8 pre-image. Okay, for your home task, for your own exercise here. No need to submit. Okay, and then try to find. Okay, try to check. Okay, which algebra here, such that your function here is measurable with respect to this algebra. Okay. Okay, I think maybe for this first discussion here, okay, I stop here for a while. Okay, try to revise back. Okay, try to recall back, try to study Prof Nasir's class. Okay, Prof Nasir's discussion, and I hope that my explanation here will help you, okay, to understand Prof Nasir's class. Okay, next time I will consider another type of discussion. Okay, so thank you very much.